Hello, and welcome to the Academy of Useless Ideas. As mathematicians, we often develop a sense of aesthetics that is as hard to explain as why pineapple on pizza is so controversial. But one thing we can all agree on is that our curiosity often leads us to fascinating concepts in analysis. Today we'll delve into one of those concepts, uniform continuity. But first, let's tackle a concrete problem: finding continuous extensions of a function. Trust us, it'll be worth it. An extension of a function f from x to y is simply a function f tilde that takes a superset curly x of x as its domain, and where f tilde restricted to x is equal to f. Think of it as stretching out the function to a larger canvas. To give you a concrete example, consider three functions: sin x over x, 1 over x, and sine of 1 over x. All of these functions are defined on the real numbers except at 0, but we can extend their domains by assigning any value we want at 0. However, if we want to maintain some of the properties of the original function, we need to find a continuous extension. Can we do it? Let's find out. We can extend sin x over x by assigning it the value of 1 at 0, and this is the only way to extend the function continuously. The trick is to take the limit of the function as x approaches 0. But when we try to extend the function 1 over x in the same way, we hit a roadblock. As x approaches 0 from the right, the function shoots up to infinity, and as x approaches 0 from the left, it plunges to negative infinity. There's no single value we can assign at 0 to make the function continuous. You might think that we can't find continuous extensions when the function is unbounded, but that's not quite correct. Take the function sin 1 over x, for instance. It's bounded, yet we can't extend it continuously to 0 because it oscillates too widely around that point, and the limit simply doesn't exist. As always, in our never-ending quests for mathematical beauty, we want to find a criteria for when continuous extensions are possible. But before we can tackle this question, we need to clarify it as much as possible. So let's start with the simplest version that will still yield some juicy insights. Suppose we have a continuous real-valued function f defined on a bounded subset x of the real line. Can we always find a continuous extension of f over the closure of x? We focus on bounded sets to avoid the complications that arise when the independent variables grows to infinity. Plus, we only need to extend the function to the closure of x because the limit of a function is only defined for the limit points of its domain. Let's zoom in on the problem of extending f to just one limit point of x. Suppose x is a limit point of x that isn't already in the domain of f. To extend f and make it continuous at x, we must define f tilde at x as the limit of f of x prime as x prime approaches x. The hitch with this definition is that the limit might not exist, so we need a condition that guarantees the existence of the limit. At this point, we might try playing around with the definition of limits to see if it yields any insights. But as with any exploration, we may hit a dead end. In this case, the definition references the limit itself, which is exactly what we are trying to find. One idea could be to take a page from Cauchy's book and modify the definition to avoid mentioning the limit. However, we'll take a slightly different path. When one is stuck doing mathematical research, it can be useful to make a list of all equivalent statements in the hopes that one of them will shed some light on the problem. In this case, we might recall that the limit of a function at x exists if and only if there exists a point y such that for every sequence xn converging to x, the limit f of xn converges to y. In other words, the limit exists if no matter how we approach the point, the limit of the function is always the same. Let's explore what would happen when there are two different sequences, xn and x'n, converging to the same point, but such that the sequences f of xn and f of x'n converge to different points. Since xn and x prime of n converge to the same point, we note that their difference converges to 0. On the other hand, the difference between f of xn and f of x prime n doesn't converge to 0. Combining those facts, we can postulate the following conjecture. The function f cannot be extended continuously if there exists an epsilon greater than 0 such that for every delta greater than 0 there exists x and x prime in x such that the distance between x and x prime is smaller than delta, but the distance between f of x and f of x prime is greater than or equal to epsilon. Note that in this conjecture, delta serves as a witness for x and x prime to converge to the same point, while epsilon serves as a witness that f of x and f of x prime do not converge to the same point. It is important to remember that a sufficient condition S for a statement n is one that implies n. On the other hand, a necessary condition n of a statement S is one that is implied by S. In other words, a sufficient condition guarantees the truth of the statement, while a necessary condition is guaranteed by the truth of the statement. Therefore, if our conjecture is true, we have found a sufficient condition for the existence of a continuous extension. We can show this by writing the contrapositive of the conjecture. It turns out that not only is the conjecture true, but if we limit ourselves to bounded sets X, the condition is also necessary. In other words, a real-valued function f over a bounded set X admits a continuous extension to the closure of X if and only if for every epsilon greater than 0, there exists a delta greater than 0, such that for any x and x prime in X, if the distance between x and x prime is less than delta, then the distance between f of x and f of x prime is less than epsilon. While we won't be proving this enhanced conjecture today, it's not our goal either. Instead, we're here to motivate the definition of uniform continuity. A function is deemed uniformly continuous if it satisfies the second condition we've discussed. Sure, we could have a start with this definition and went on to highlight some of its properties, but that wouldn't make for an engaging discussion. We wanted to emphasize that mathematical ideas, just like any other idea, are born out of human curiosity and problem solving. Every definition you come across in math is a product of human ingenuity, with some practical purpose in mind. As time passes, we sift through the good from the bad, and the fact that uniform continuity is still a relevant topic in analysis suggests that it has some fascinating uses. Comparing the definitions of continuity and uniform continuity side by side can be useful. The main difference is that in uniform continuity, the quantifier of the point of continuity comes after the selection of delta. This means that uniformly continuous functions are continuous and that delta selection is independent of the point of continuity. Hence the name uniformly continuous. You can select the same delta uniformly for the whole function domain. Additionally, from our motivating example, we can see that a function is not uniformly continuous if there exists two sequences converging to the same point, but their functions do not converge to the same point. Alternatively, this fact can also be proven directly from the definitions, which is equivalent to proving one of the directions of our improved conjecture. Finally, let's consider what happens when we have a continuous function over a closed and bounded set. In this case, the function is already a continuous extension over its closure. Using our improved conjecture, we can see that a continuous function over a closed and bounded subset of the real numbers must also be uniformly continuous. It's worth noting that closed and totally bounded sets of a complete metric space are compact, so we can state the following theorem. A continuous function over a compact space is uniformly continuous. While you could prove this theorem directly from the definitions, it's much easier to see why it must be true when you understand that uniform continuity is precisely what's needed to produce continuous extensions over bounded sets.